Hello students, in differential calculus we have studied about the function, and the function we have defined, let a and b be two non-empty sets. Then a function f from a to b is defined to be a rule which associate with each value of x belonging to a given value of y to b. Now in this chapter of homomorphism of group, will study a function from one group to another group. There will be from one group to some other group, or from the one group to the same group, and defined the homomorphism. What is homomorphism? Homomorphism is a mapping, just mapping. For that, we need is mapping is a function mapping, or it's a function. So function we know we need two known presets for the function, but for the homomorphism we need two groups. So let us consider let G with binary to O and G dash with binary to G star be two groups. Then a mapping or a function f from G to G dash is called a homomorphism if f of a composite with b is equal to a composite with b in G. Let composition with b of G is equal to fa composition with fb. This is composition of image set G dash. Composition of image set G dash. G dash. Now, now let me understand this thing from this diagram. Now, this is G, equal to G. Suppose it contains, and let us take L2 elements A and B belong to G, and the composition of G is a group with composition this O. So A composition B is also element of G because G group, close property of group. Now G dash is another group with composition G star and Fa. If F is a mapping from G to G star, then F takes element A to Fa, and F takes element B to Fa. And F takes element F takes element A comes to B to the Fa composition with star comes with Fb composition with. So this is the, so this mapping. What is mapping? If this situation holds true between the two groups, mapping is just between the two groups. This mapping is called homomorphism. Then what is homomorphism? Then a mapping or a function f from G to G dash is called a homomorphism if f of AB, f of A, f equals to B is equal to FA composite FB. Composition G in the domain set of F, the composition of G set, and in the range set of F, the composition of G dash. If the binary operation of both the groups G and G dash is same, then we define homomorphism as a function f from G to G dash, such that f of A is equal to fa. This is what we got about the what is homomorphism. Now we'll understand how many types of this homomorphism are. We know that the function are type 1 1 on 2 into many. But in the case of the homomorphism, homomorphism is a mapping f from G to G. What is this? Homomorphism is again a mapping from the group G to group G dash. This homomorphism, this mapping from G dash, which is homomorphism. This homomorphism is called is a epimorphism if it is onto. If this homomorphism is onto, it is called epimorphism. If this homomorphism from G to G dash is 1 1, it is called isomorphism. If if this mapping from G to G dash is a homomorphism, and number one homomorphism, number two it is 1 1, number three it is on 2, then we say that the two groups are isomorphic groups. If we define a mapping on these two groups G and G dash, and if this mapping is one, this homomorphism as well as 1 1 and on 2, so then we say that these groups are isomorphic groups. But if this mapping from G to Z, if this mapping from G to G dash is homomorphic, number one, and on 2, it is called epimorphism. If this mapping from F from G to G dash, it is homomorphism as well as 1 1, it is called isomorphism. Now, if the mapping is from G to same to G, if mapping from G to G, which is a homomorphism, if mapping from G to G, G to same to G is homomorphism, then this mapping is called endomorphism. If this mapping from G to G dash is homomorphism as well as 1 1, it is called automorphism. Mapping from G to G, G to same group to G, it is if this mapping is homomorphic as well as 1 1, it is called automorphism. Homomorphic groups. A group G dash is called a homomorphic image of a group G if there exists a mapping G F from G to G dash which is onto as homomorphic. Then G is called homomorphic image of G. G dash is homomorphic image of G. Now we have studied the type of homomorphism. Now let's define kernel of a homomorphism. Let G and G dash be two groups and a mapping F from G to G dash be a homomorphism. Then kernel of F is a set of all x belong to G such that F is equal to E dash. So all elements belong to the set G, all x belong to G such that whose image under the mapping F is equal to E dash, where E dash the identity element of G dash. Mapping be a homomorphism must be let G and D be two groups and mapping function f from G to G is be a homomorphism. First is mapping homomorphism, then if f is a homomorphism, then kernel of f is the set of all x belong to G so that f of x is equal to E dash, E dash the identity element of G dash. And it is where KER of f. Now look, we have to, if f is on 2, then range of f will be G dash. F is on 2 means every element of G dash as if imagine every element of G dash if imagine G. So this is then the range of f will be G dash. When f is 1 1, then kernel of f is equal to f or f inverse of E is equal to E. Kernel of f consists of the identity element. If f is 1 1, then kernel of f is a homomorphism, and kernel of f consists of the identity element of G. Basic things of homomorphism. So, if F be a homomorphism from a group G into a group G dash, then F of E is equal to E dash, where E and E dash are identity elements of G and G dash respectively. Second is F of E inverse is equal to F A whole inverse for all A belongs to G, and F of A raised to N is equal to F of A whole raised to N for all N. Let's go first. What is given? F be a homomorphism of a group G into the group G dash. Then we prove F of E is equal to E dash. First part is given is mapping F from G to Z is a homomorphism. It's a homomorphism given to us. Now E belongs to G. E belongs to E. E belongs to G implies F of E belongs to G dash. because f is mapping G to G dash. E is element of G. So f is mapping G to G dash means f takes element of E to G dash. Element of G to consider all A belongs to G implies f of A belongs to G dash. If you take this mapping, if you print this from the mapping f on all the elements of G, then fa will be the elements of G dash. Since E dash is the identity element of G dash, therefore f of A is the element of G dash. F of A into E dash is equal to f of A because G is equal and this is equal to A contains A is the element of A is element of G and E is element of G. A is equal to A into E. Now f of A into E is equal to f of A into f of E. G because G is there, A is equal to AE because G is a group and there is the element of group and they don't take is equal to same. A2 is equal to A is equal to A into E and this is homomorphism for f of A. This implies this equal to this equal to this equal to first and last. This implies f of A into E dash is equal to f of A into f of A. Now G dash is a group, so they are the elements of groups. So cancellation law, left cancellation or right cancellation of origin G dash. So now apply right cancellation law by f of A inverse. So f of A inverse into f of A is equal to E into E dash. E dash into E dash is equal to E. So f of A inverse into f of A is equal to E. E dash into f of E is equal to f of E. So this comes out to be E dash is equal to f of E. Then using this is equal to the second part. For all A belongs to G, consider E is equal to for all A belongs to G. E dash is equal to f of E. E can written as E is the identity element of G. So A is the element of G. So A into A inverse A into A inverse is equal to E is equal to A inverse into A. So E can written as A into A inverse because f is a homomorphism. So f of A inverse is equal to f of A into f of A inverse. Similarly, we can also write E z dash is equal to f of E. E can written as A into inverse is equal to A inverse into A. E can written as because A is the element of G and G is equal. So this is equal to this. Now this is f is a homomorphism. Therefore, f of inverse into A is equal to f of inverse into f of A. First and second implies f of A to f of inverse is equal to E dash is equal to f of inverse into f of A. So what this implies? This implies if A into B, A into B is equal to I is equal to B into A, then B is equal to A inverse or A is equal to B inverse. So this implies f of A is equal to f of A to f of A inverse is equal to E dash or f of A inverse is equal to f of A implies f of A inverse is equal to f of A whole inverse is equal to f of A inverse. Implies the second. Now the third result to prove is f of A raised to n is equal to f of A whole square. We'll prove it by the method of wonder principle method inversion. Let n is equal to 1. So f of 1 is for 1 is equal to f of A whole square. Implies f of square f of A which is 2.0. Now let us assume that result is 2 equal to k. That is f of A raised to power k is equal to f of A whole square. F of A whole square. In order to show that the result is true for n is equal to k plus 1, we have to show that f of A is for n plus k is equal to f of A whole is for n plus k. Taking left hand side. F of A is for f of A is for n k plus 1 is equal to f of A into f of k into f of 1. F is for k. Now this is a f is a homomorphism, so we can write this is equal to f of A is for k into f of A. So this is equal to now substitute the value of f of k. This is equal to f of A raised to power k given f of A raised to power whole square k. This is equal to 1. So this comes out to be f of A raised to power k plus 1. It's equal to right hand side. Result is true for n is equal to k plus 1. Conclusion from this is We have proved the result is true for n equal to 1, the first step, and assumed the result is true for n equal to k, the second step, and also proved the result is true for n equal to k plus 1. Hence, Howard's laws, the value of k implies result is true for k plus 1. Hence, it continues for all values of. Thank you very much.